Or I get started.
Well, I would quickly say a few words about InSIS,
Thank
okay?
you.
Since you asked about this, okay.
Right.
So, good evening and welcome to all the attendees of this 26th webinar of InSIS from the Indian Structural Integrity Society. This was started about 2 years ago, and we have been able to successfully roll out every month. Uh, Periodicity one lecture by eminent speaker from the domain. It can be from a variety of specializations as well as from the bandwidth of people from various countries and their organization levels. So this is being the 10th year of our society. It makes it all the more, interesting to say that we have been able to sustain this initiative of this InSIS webinar. We started about 2 years ago till today, and I hope that we will be able to do more. And I request the audience to participate actively in these webinars. Thank you very much. Over to you, Nanda.
Thank you, Raghu, for that introduction. Some housekeeping rules. Please keep your cameras and mics on silent, and you can raise your hand perhaps at the end of the discussion, and then you can ask your question. With that, it's my pleasure to introduce our speaker for today. Dr. Punit Kumar is a postdoc in Professor Rob Ritchie's lab at Lawrence Berkeley National Labs and at the University of California, Berkeley. He's been kind enough to log in from there. It's probably very early for him this morning. Puneet received his bachelor's and master's degree in metallurgical and materials engineering from the National Institute of Technology, Rourkela. He did his PhD on the fracture and fatigue behavior of additively manufactured titanium alloys at the Department of Materials Engineering at the Indian Institute of Science, Bangalore. He was awarded the ACTA Student Award in 2019. He continued as a postdoc in NTU Singapore, where he studied mechanical properties of various conventional structural alloys, which were made by additive manufacturing. In LBL, he is continuing to investigate the fracture behavior of high entropy alloys in extreme environments. And he's going to tell us a little more about his work from his postdoc. And with that introduction, I'll just hand it over to Puneet. Thank you for agreeing to give us this seminar.
Thank you, Professor Namta, and thank you for this opportunity to you and Professor Raghu Prakash and Ma'am Deepa Srinivasan. So let's get into the webinar. Uh,
Can you put
yeah,
your slides on full screen mode, please?
yeah, I think I have done that. I'm not sure if you
Uh,
can.
on my screen, it's still, I can see your slide sorter on the site.
Okay, let me try that. Something else then.
I think you have to share the window of PPT show,
Yeah.
PowerPoint show. Yeah.
So now the sharing is gone. You'll have to redo the whole thing.
Otherwise, on this screen itself, you click on FI. Yeah, good,
There we
good.
go.
It has
It's
come. Yeah.
now it's perfect. Okay, over to you. Thank you.
Okay, thank you, ma'am. Yeah. So, okay, so let's start the webinar. In today's webinar, I'm going to talk about a next generation of structural materials, especially suitable for extreme environments. So, to start with, first I will talk about what is the motivation. Why do we want to discover these new structural materials? And this is where I will talk about damage tolerance in structural materials and what is the origin of strength versus toughness trade-off that we usually see in structural materials, usually metals and alloys. And then I will also talk about conventional ways of strengthening and toughening materials. And since today's webinar is going to be about additive manufacturing and high entropy alloys, I am going to introduce these two topics briefly. And then the main body of my presentation, I've divided it into two parts. In part one, I will talk about additively manufactured materials which are suitable for their application in ambient and cryogenic temperature condition. In the second part of my presentation, I will talk about refractory high entropy alloys which are suitable for high temperature applications. So why do we want to discover new structural materials? So what is the requirements, that what are the applications where we need to use these structural materials, and where uh, existing materials are not sufficient? So if I want to give an example of a cryogenic temperature application, one of the foremost application would be these rocket engines, which are operating at cryogenic temperatures, because you need to store both oxidizers and fuels below their boiling point. For example, methane has boiling point about 111 Kelvin. Oxygen has boiling point about 90 Kelvin. And at the same time, these fuel also apply some pressure on the fuel tank. So if you are making a fuel tank of these rockets or cryogenic engines of the rocket, you need to store these fuel at really cryogenic temperature. So the structural material should be able to withstand those cryogenic temperature as well as these pressures. Other than that, if we want to, for example, use green hydrogen, then in the storage and transport of the green hydrogen, the most efficient way is to store them also in the liquid form. So that's also a useful, or that's going to be a popular place where we need to have a structural materials which can survive cryogenic temperatures. Or even recently, actually, Rolls-Royce, they are trying to develop these engines where they want to use jet engines, where they want to use green hydrogen, and they have realized that they can only store these fuels at cryogenic temperatures for having most fuel efficient jet engines. So that's, they are also looking into these structural materials which can survive both cryogenic temperature as well as embrittlement from hydrogen. So the second example I want to give is about high temperature structural materials, and the foremost example of that would be the jet engine. And usually, most of us know, if we run the jet engine at higher temperature, the hotter the better. The jet engine will be more fuel efficient because of this Carnot equation. And if we look at the development of materials that are being used in jet engine, we see in the start, or in the beginning, we were able to discover these newer structural materials which were able to survive more and more, or higher temperatures. And because of that, we were able to follow this line of ideal performance. But in last 50 years, what we have been able to develop these better engines, but we were able to do that through developing these cooling technologies, such as internal channels or thermal bond coat. But because we are not developing new materials, there is one inefficiency loss. And if we want to reduce this inefficiency loss, and we want to develop a fuel efficient jet engines, then we have to try to come up with newer structural materials which can survive these extreme temperatures. So these structural materials would be also suitable for supersonic jet engines, which can be used for civilian, military, as well as space travel. So if we want to develop structural materials for these conditions, extreme conditions, so what do we need in these materials? So these materials should be damage tolerant. And when I say damage tolerant, what does it mean? It means that materials should be strong, which means they should be resistant to plastic deformation. And these materials should be also tough, which means they should also be able to resist fracture. So if we talk about what is fracture, or how materials fracture, so the idea, we can take this basic idea of Rice and Thompson model, where they say that if you have a crack, and if you apply stresses behind at the crack tip, and in that case, if you break an atomic bond ahead of the crack tip, it means that your material will fracture, or the crack will grow inside the material. So this is the basic idea of fracture. But if we look inside metal and alloys, if we extend the same model to these materials, then when you apply a stress at the crack tip, in this case, instead of breaking an atomic bond, what will happen is that you emit a dislocation from the crack tip, or if you have a dislocation source ahead of the crack tip, that will emit a dislocation and it will end on the crack tip. And as you can see, when you emit a dislocation, or you have some dislocation activity at the crack tip, you see now your crack tip is blunted, and you need to apply even higher stresses to grow the crack. So this is the origin of the strength versus toughness trade-off that we usually see in metallic materials. And for example, if you have materials with so higher yield strength, it means that you will have lower dislocation activity at the crack tip, and that means you will have lower fracture toughness. At the same time, if we have materials which are which have lower yield strength, which means you will have more and more dislocation activity at the crack tip, those materials would have a lower will have higher fracture toughness. And we can also divide these further into these two broad categories. There are many exceptions to this, but if we just go and divide it in broad categories, what we can divide is in BCC alloys, because the material is not closed pack, in nucleation of dislocations or movement of dislocations or other defects, it's slightly difficult compared to FCC materials, and that's why these materials would have higher yield strength but lower fracture resistance. And at the same time, FCC alloys, which has these closed packed crystals, in those materials you would have it would be easier to nucleate dislocation and move dislocations, and that's why we will have higher fracture resistance but low yield strength. So if we talk about conventional ways of uh, developing new, or we talk about alloy development, different types of alloy we want to develop. So if we want to develop FCC alloys, what we need to do in this case, the strategy we need to have is that we want to increase their yield strength without affecting the fracture resistance. So conventional ways of achieving this is, for example, the first one I want to highlight here is precipitation strengthening. What you can do is you can put these precipitates inside the material, which can block the movement of dislocations, and you can increase the strength of the material. But at the same time, what happens if you have a crack inside these materials, these precipitates would also block the movement of these dislocations. And because of that, what would happen is that you want to achieve this type of property improvement, but actual trend would be where while you increase the yield strength, you will also see losses in the fracture resistance of the material. The second way we can achieve a strengthening, or we can do strengthening of FCC alloys, is that we can try grain refinement through material processing. And in this case, there are two possibilities. For example, what can happen is that your grain boundary is blocking these, or blocking the movement of this dislocation that would increase the strength by this hall pitch mechanism. And at the same time, what can happen is that you can nucleate a different slip system in the neighboring grain, and by doing that you can still spread the deformation or plasticity or damage away from the crack tip through these route. And this usually happens if you have grain boundary which are in low angle grain boundary. And if in comparison, if you have grain boundaries which are high angle and they don't allow transmit of dislocation across the grain boundary, or activate newer slip system in the neighboring grain, in those cases you might might be nucleating micro voids on the grain boundary. So there are two possibilities in this case. You can in some cases improve the yield strength without actually significantly affecting the fracture resistance, but in some cases you will be affecting the fracture resistance. Also, it's very difficult to control the characteristic of the grain boundaries through metallic processing that we have, existing metallic processing we have. So that's another challenge when we want to design newer materials with higher strength and higher fracture resistance. So in BCC, in case of BCC material, what we want to do is we want to increase their fracture resistance without affecting the yield strength. And usually there are two ways we can achieve this in BCC materials. We can have extensive toughening from tortuosity to the crack path. Usually what I mean by that is, usually BCC materials, they fracture by cleavage fracture or intergranular fracture. And if you have this crack path which is tilted or twisted, in that case you can have a higher fracture resistance in this material. Although these improvement in fracture toughness because of these extrinsic mechanisms are not as much as what you can achieve through intrinsic toughening. So in BCC alloys also you can have some intrinsic toughening by what you can do is you can have compositional modulation that can allow defect nucleation or movement of defects. For example, in tungsten, if you add more and more rhenium, you can ductilize tungsten. So those mechanisms also work in improving fracture resistance of BCC materials. But the problem with that is that you will also be affecting the yield strength of these materials. So what I want to talk about today is how can we deal with these trade-off with these relatively newer technologies such as additive manufacturing or high entropy alloys. So this is where I want to briefly introduce these two topics before getting into my main body of presentation. So the method that I want to talk about today, additively manufactured method, is laser powder bed fusion process. I'm aware most of you might be aware of this. Most of you might be aware of this methodology. So I will briefly go through this uh, additive manufacturing process. So in laser powder bed fusion process, what you do is you take a laser beam. Essentially, you are melting the material line by line, layer by layer, and you are building a 3D part. And usually you can achieve through this process where you have these powder delivery system where you spread the powder on the powder bed, and you use this scanner to melt the material, selectively melt the material, and you get a final 3D component by lowering this powder bed of layer by layer. So there are several process parameters that are important in this additive manufacturing process. For example, laser power, how much power you are giving to the material during the process, that decides how much material you are melting in each uh, line when you are melting the material. And at the same time, the other processing parameters would be layer thickness. So what is the thickness by which you are spreading the powder and melting the material in each layer? And then other parameters would be like hatch spacing. So what is the spacing between two subsequent lines of these laser scans? And then the scan rotation is one parameter where which decides, like, in this layer you are melting the material going in this direction. Next layer you can rotate the scanning direction, and that is what is referred to as scan rotation. And scan speed is how fast your laser beam is moving over the material during melting them. So that's what is scanning speed. And there is a parameter which is called volumetric energy density, and it is a combination of process parameter, which is laser powder divided by thickness, hatch spacing, and scan speed. And this is usually, this has unit of joule per millimeter cube, and this is usually used for reducing the porosity or optimizing the density of the additively manufactured materials. So there are a few possibilities during additive manufacturing, and I want to talk about what are the ways which we can control the microstructure during additive manufacturing process. So I've divided it into two parts. The first part I refer to as direct effect, which is basically, essentially, additive manufacturing is a building process where you are melting the material line by line and building each lines and each layers to get a final 3D part. And when you have this building process, you would have a signature of this building process, and then signature comes from you have a melt pool when you are melting the material, and this melt pool can have the signature effect. For example, this is image of titanium 64. And in titanium 64, usually when you are in this case we were using the scan rotation of 90-degree, and because of that you can see the scan is overlapping after each another layer, and because of that you can have these long columnar grains, and on the top you can see the microstructure reflects your hatching strategy. So this kind of microstructure is what I'm referring to as mesostructure, and this is a signature effect of the building process that we are using. And the second effect I would talk about is indirect effect. For example, in additive manufacturing, you are using high power laser beam, and you are melting a small volume of material. Because of that you have very high thermal gradient and very fast cooling rate, and because of that material solidifies by forming this cellular structure, and the growth of this cellular structure depends on the direction of thermal gradient. And as a consequence of that, this is the cells in actual material. This is 316L. You can see the cellular structure, and these cells are essentially single crystal growing in the direction opposite to the thermal gradient. And the direction of thermal gradient you can control by controlling how fast your laser beam is moving and what is the laser power. And here I am showing two examples where direction of G is changed from here is below the G direction is going in the way the red line is showing here, and here the G direction is perpendicular to the plane. And what is happening here is that when you rotate your G, you can rotate this direction of the cells, how they grow. And here you can see when your cell is growing this direction, you are having a 0, 1, 1 texture. And if your cell is growing perpendicular to the plane, you are essentially growing a crystal in 1, 0, 0 direction. And by doing this, you can have a very good control over texture of the material. So this is what I wanted to highlight as the indirect effect on the microstructure of material. So this kind of control you have in additive manufacturing, which usually doesn't exist in conventional manufacturing processes. So coming to high entropy alloys, so high entropy alloys basically comes from the idea is that you take multiple principal elements, and if you mix them, you have several possibilities. For example, you can end up with this intermetallic and solid solution, or you can have multiple solid solution. There is a possibility of a spinodal decomposition also, but you can also end up with single phase solid solution. This essentially happens when your delta H formation, enthalpy of formation of compound is lower than configurational entropy that you increase by mixing multiple principal element in large amount. And essentially you can see from this formulation that usually we refer to this single phase solid solution as high entropy alloys. But if you have possibilities of forming compounds, and in terms of like having a higher delta HF, then in that case, instead of having single phase solution, you might end up with this intermetallic and solid solution. So essentially high entropy alloys are not only high entropy alloys, they are also enthalpy stabilized alloys, where you have to carefully select these principal elements so that your entropy of forming these intermetallics is also enthalpy of forming these intermetallic uh, phases is also minimized. So while we are referring to these materials as high entropy alloys because it has become very popular, it is essentially you are lowering the chances of having these intermetallics with a higher enthalpy of formation. So why high entropy alloys are special? So there are many reasons people will give you, but I want to go through these reasons which I think is quite interesting and quite uh, popular. The first one is when you are mixing multiple principal element alloys. Earlier in conventional alloys, we were looking at the corner of the phase diagram, and now because we are mixing large amount of these principal elements, we are in the center of the phase diagram. So it opens up a large compositional space for us to explore and try to see if we can have better materials or newer materials with better properties. So this is what gives us opportunity to do a lot of research in this field. The second example I want to give is this formation of short range order. So usually when you mix a lot of these principal elements or a lot of these elements, what you would assume is that you might have a quasi-random structure where these, for example, here I'm talking about chromium, cobalt, nickel. You would assume that chromium, cobalt, nickel will randomly choose the positions in the unit cell, but in reality, there is a possibility that some elements might like to sit next to each other, or some element might dislike to sit next to each other. For example, in chromium, cobalt, nickel, people have done this first principle calculation, and they suggest that chromium doesn't like to sit with chromium, another chromium atom, and then you can end up with these order structures where you have a layer of chromium, then you have layer of cobalt, nickel, and this way you can have this small short range order, and the sequence of this short range order is huge. For example, chromium, cobalt, nickel, if you look at these elements, chromium is BCC here, cobalt is HCP, and nickel is FCC. And when you mix all these three and you end up with this FCC, chromium, cobalt, nickel has FCC crystal structure. So people did this first principle calculation, and they realized that actually this material should never be stable as FCC alloy at room temperature, because you have negative stacking fault energy if you calculate those two first principle calculations. And the way they can actually realize the formation of these FCC crystal is by inducing this ordering inside the material, which increases the stacking fault energy to stabilize the FCC phase. And the other consequence of this is like In binary alloys, the formation energy or nucleation energy of defects is constant if you have a binary alloys. But in case of high entropy alloys, depending on the extent of these ordering or the type of these ordering, you can have a range of formation energy of defects, and that can have a huge consequence in terms of deformation mechanism when you are deforming these materials. So that these two examples is what I find really interesting about high entropy alloys. So getting to the main body of today's presentation, the first part I want to talk about additively manufactured materials which are suitable for ambient and cryogenic temperature application. The first alloy I want to talk about is titanium 41 niobium, which is a beta titanium alloy and which is suitable for biomedical applications because of its lower elastic modulus. And the second alloy is a high entropy alloy which is suitable for cryogenic temperature applications. So when we were printing this titanium 41 beta niobium beta titanium alloy, we wanted to essentially achieve this in situ mixing, where we took this titanium powder and niobium powder and we were mixing them and putting inside this LPBA processing unit, and we were trying to see if we can form an alloy by melting this mixture of the powder. There is one challenge that comes with that, is that titanium has a lower melting point, significantly lower melting point compared to niobium. So to melt all the niobium, you have to apply a lot of higher volumetric energy density inside the material, and when you do that, you might end up with this unstable melt pool which leads to formation of keyhole pores. And if you try to reduce the volumetric energy density, essentially you might have a lot of unmelted niobium particles you can see here. So there is a porosity and inclusion dilemma that you are dealing with. So this is where the PhD student I was working with came up with this brilliant idea. So in case of this is normal processing techniques where you see the melt pool, the way laser beam is moving is the speed is really slow and you have a stable melt pool. He came up with this idea is that we can input a lot much more energy inside the material and have a stable melt pool if we significantly increase the laser scanning velocity. And when we did that, we were able to actually significantly reduce both. This is the example you can see, reduce both porosity and melt most of the niobium particles, because we were having this high volumetric energy density now during processing this alloy. Although there was one unintended consequence of this, that if you look at these layers of the material we were able to process, you see the top part of one layer, you have melted all the niobium, but in the bottom section of the same layer, you can see some niobium particles, unmelted niobium particles, and you can see this across the layers. And because of this, what happens is that in one region, you have material with solid solution with a very high amount of niobium. In the other region, in the solid solution, you have less niobium. So there is a compositional variation from layer to layer because of this processing technique that we used. And then we went ahead and we did some mechanical testing, starting with tensile testing of this material. And one of the thing what we observed was that this material was showing really low plasticity. It was showing higher elation compared to the same similar composition beta titanium alloy, but it was showing no ductility at all. And when we looked at the fracture surface, we saw cleavage fracture, and in side surface shows the cleavage planes are specific cleavage planes where usually BCC material fractures. So we are trying to understand what is going on. Why do we have such poor ductility in this material? So we did some TM and we saw this large omega particles present in this material. So omega phase forms in beta titanium alloys. There are several variants, and there are two which are important. If you have a small omega collapse extent, in that case this is what the structure you form, and in this case you can have some homogeneous plasticity. But if you are achieving this large omega collapse extent, which usually happens by forming these isothermal omega, if you age your beta titanium, and in this case because of the structure of this omega phase, you have heterogeneous plasticity. And in our material, what happened when we were trying to print these blocks, we were looking to do fracture toughness tests. So we went ahead and we printed these huge blocks, and printing one block was almost taking couple of days. And when you are printing such large blocks, the temperature of the blocks printed material goes very high, and essentially we were aging our material or our blocks for long time. And if you age this kind of composition above 300 degrees C, then you form this isothermal omega, which can have such effect where you have heterogeneous plasticity. And we also verified this by printing small as built coupons, and we did tensile test, and we do see plasticity. And we also tried solution treating the blocks that we had printed, the huge blocks, and we see that when you do that, you lose significantly your strength. So that was something that we did not want to see. So we went ahead and tested these large blocks, and we did some fracture toughness test to understand what would be the effect of this compositional gradation that we have in our sample. So we took these blocks, huge blocks, and we created these notches in different direction to see how it interacts with the these lines here represents the compositional gradation inside the block, and you can see how they are oriented differently with respect to the crack path. And in this case, you can see crack path would not interact that much with this compositional gradation, the lines of this compositional gradation inside the phase. And you can see here the fracture toughness is around 22.6 megapascal root meter. In other two direction, actually the fracture toughness almost doubles. And looking at the fracture surface, we see that in case where the crack path does not interact with these low or niobium poor regions, and you can see a lot of these cleavage, flat cleavage fracture surface, and that is why the fracture resistance is much lower. In other two direction, we see here, this is how the niobium poor region is oriented, and you can see when the crack goes through these regions, you have some plasticity. Again, here you can see the same thing where these are the lines of niobium poor regions, and you can see plasticity in those regions. So that is what explains the significant difference in the fracture resistance of this material. And also beta titanium alloys with omega precipitates usually show fracture toughness about this value, but because of compositional gradation, we are able to achieve almost double of the fracture resistance what we get usually in these omega precipitated beta titanium. And also during pre-cracking of this material, we see the same thing. When the crack goes through, it doesn't interact with niobium poor region. You can see very limited plasticity. In cases this is niobium poor region, you can see there is a lot of these slip bands that forms. And what happens usually at ahead of the crack tip, you form these slip bands, and the crack propagates through these slip bands, and that's why it goes through this tortuous path. And in this case, when the niobium poor region is perpendicular to the crack growth direction, you can see when it interacts with these niobium particles in these regions, you can see crack bifurcation happening, and that has some consequence on the fatigue crack growth rate also, in terms of how the crack interacts with these compositional gradation inside the microstructure. So coming to the second part of second alloy of this part, uh, I, we wanted to look through this. The idea of this project was to investigate composition something similar to chromium cobalt nickel, and the idea of this project came through this thought process that I want to talk about. So chromium cobalt nickel is a high entropy alloy which has single phase FCC crystal structure, and it shows extensive strain hardening, and which generates excellent fracture resistance. And even at cryogenic temperature, your strain hardening or extent of strain hardening further increases. Because of that, you have a fracture toughness that ranges from 210 to 270 megapascal root meter. Although this material shows excellent fracture resistance because of this sequence of deformation mechanism where you have dislocation activity, then you form these nano twins, stacking faults, and because of that, you have a large crack tip blunting happening, and which gives you such high fracture resistance. The problem with this alloy is that it has yield strength which ranges from 415 megapascal to around 625 megapascal at even at cryogenic temperature, and these strength values are somewhat similar to stainless steel. And stainless steel also have a fracture toughness around 200 to 250 megapascal root meter. So there is no incentive to actually try to go and use this material which has such a high amount of cobalt, which is an expensive element if you know about that. So the idea was that, can we use additive manufacturing to increase the strength of this material without affecting the fracture resistance? So this is where we selected this composition, where we have this additionally added iron and aluminum. And the idea of adding aluminum was that in additive manufacturing you have this huge thermal gradient that I talked about, and you are melting a small amount of material. So because of this combination of high thermal gradient and fast cooling rate, the material solidifies usually a cellular structure, as I talked about this in introduction. So when these cells are growing, you have constitutional supercooling near these cells, and because of that you have these liquid which are rich in the solute atoms. And when you add aluminum, these solute rich area becomes really rich in aluminum. And when you have these high concentration of aluminum on these cell boundaries, what will happen is that when they solidify, you might end up forming these B2 phases on the cell boundary. And especially in the regions where you have this shows a flux of solid rejection, and the highest flux would be to the cell boundary triple points. And in those regions you will have sufficiently high aluminum to form these B2 phases. And in other regions also you are having these segregation of aluminum, but they are not sufficiently high enough to form this B2 phase. So we end up with this microstructure where you have these cell boundaries decorated by B2 phase. And these regions where you don't have sufficient aluminum, these aluminum are able to trap the dislocations that form during thermal cycling of this material. So during additive manufacturing, when you are printing the material layer by layer, so the layer below the layer you are melting, they also go to really high temperature and they expand, and when they cool down they contract. And due to this thermal cycling, you form a lot of these dislocations, and the aluminum on the cell boundary, they trap these dislocations. So essentially what you end up with this cell boundary where you have these B2 phases, and these B2 phases are connected by these dislocation nano bridge. And essentially this microstructure that we formed through LPBA processing of this composition, we call it honeycomb microstructure, which also, if you look at this 3D pseudo 3D microstructure diagram, you can see it resembles this honeycomb microstructure. So we went ahead and did some tensile test on this material. And when we do tensile test, we see the yield strength at room temperature increases by 49% compared to the rod counterpart of this alloy. And at cryogenic temperature, the yield strength almost reaches 1 GPa. And so this is a significant improvement, about 50%. And this improvement in yield strength happens because now you have the cell boundaries decorated with B2 phase and these nano bridges of dislocations. So during low plastic deformation or early plastic deformation, they are able to resist dislocation movement out of these cells. And essentially these cells have this Hall patch effect that is giving you such high strength, and still you are able to maintain a good amount of plasticity even though you have improved the strength of this material. So we wanted to look at the fracture resistance of this alloy. And for evaluating fracture resistance, what we do is we go through this process of generating R curve, where we measure the load line displacement, and based on that we calculate J values for each step of crack growth. And if we draw a blunting line through these R curves, we can get this J1C value, which we can convert to KJ1C through K and J equivalence. And in this material, what we see is that fracture toughness of this material is about 300 megapascal root meter at both room temperature and cryogenic temperature. So the fracture toughness is actually even higher than what we see in rod chromium cobalt nickel, which shows fracture toughness about 200 to 270 megapascal root meter. So to get an idea what is this extent of fracture resistance in this material, we also went ahead and we did some heat treatment to actually dissolve these B2 phases on the cell boundary and have these precipitates or nano precipitates of B2 phase inside the matrix. And when we do fracture toughness test on this microstructure instead of the honeycomb microstructure, we see the fracture resistance at room temperature drops significantly. You can see the difference in the R curve, and fracture toughness is almost less than half of what we see at room temperature in honeycomb microstructure. And at cryogenic temperature, we see that fracture toughness is even significantly reduced and is almost 6 times less. And after certain amount of crack growth, about zero point 0.2 to zero point 0.3 we see the material fractures by unstable crack growth. So the fracture resistance is significantly lower. And if we compare these fracture toughness value with respect to the other known alloys, we see this material shows higher fracture resistance than cryogenic steel, and it also has higher strength on specifically designed cryogenic steels as well as stainless steel or this chromium cobalt nickel based high entropy alloys. And if we compare, you can directly see precipitate strength in these high entropy alloys and how it improves when you have this honeycomb microstructure. So what is so special about that this microstructure that is giving such high fracture resistance to this material? So to understand that, what we do is we take one CT sample and we section it from the center to expose the region of high stress triaxiality. And in this region, we see that we do this EVST and we did this strain mapping. And looking closely at this crack tip, we see that these misorientation bands you can see here also, they are emanating from the crack tip and they are traveling further away from the crack tip, almost around 200 to 300 micrometer. And if you look closely, you can see these misorientation bands are actually traveling in between the B2 phases on the cell boundaries. And if you do TM, you can see the same thing again here, where these openings of where you had these nano bridge of dislocation, they break down, and you can see dislocation traveling through these openings channels, and they are traveling further away from the crack tip. So essentially what is happening is that early phase of plastic deformation, these cell boundaries, they are able to resist plastic deformation. But in case of severe plastic deformation at the crack tip, these nano bridges connecting the B2 phase, they break down and they allow the movement of these dislocations away from the crack tip. So you are able to distribute damage away from the crack tip, at the same time you are also able to have high strength in this microstructure. Comparatively, if we look at this heat treated material, we see that these strain map shows that you can see dislocation activity only about 10 to 20 micrometer near the crack tip, and these dislocations are not able to travel away from the crack tip, giving you a relatively poor fracture resistance, much lower fracture resistance in this microstructure. So with these two examples, I come to concluding remark for the part one of my presentation. So here what I want to highlight is that if you look in natural materials, for example, in bones, you have these several features of different length scale, which gives you different mechanisms resisting fracture. For example, these molecular uncoiling at micro level can give you micro cracks. Fibrillar sliding can give you these crack tip bridging happening, or you can have micro cracking on these mineralized collagen fiber fibril, giving you these multiple crack forming ahead of the crack tip, which can also give you fracture resistance. And the same goes with osteons, which can deflect the crack to give you extrinsic toughening. So you see, nature has built this material bottom up, and they have introduced these different features of different length scales that give you fracture resistance as well as combination of other properties that you want. So in conventional method, which is a top down approach, we are not able to generate these different features of these different length scale in the microstructure. But additive manufacturing provides this opportunity, where I gave these two examples in today's talk, where we have these intrinsic toughening through the cellular structure that we can control their size and shape, and we can try to get material more tougher, or we can increase the fracture resistance. At the same time, compositional gradient inside titanium 41 niobium also gives you extrinsic toughening through crack path tortuosity. There are other studies that I have done where we see laser scan tracks deviating the crack to give you extensive toughening, or in TI64, depending on the melt pool, you have these microstructure where you can have crack tip tortuosity. So there are examples where you can, in additive manufacturing, you can put these structures at multiple length scales, and you can have these combination of properties which are usually difficult to achieve through conventional routes. And the main challenge, although with this additive manufacturing process, is that all these combination of microstructural features that you want to develop, they are interdependent on processing parameters. So you would have to do a lot of studies, a lot of investigations to come up with this optimum microstructure for having these combination of properties. So, coming to the part two of my talk, I want to talk about the structural materials which are suitable for high temperature application. And here I have selected these two alloys, which is you take a group 5 elements, niobium and tantalum, and then mix them with group 6 elements, moly and tungsten. So the first one is niobium, moly, tantalum, tungsten. Second one, we are again taking group 5 elements, but we are mixing them with this titanium, hafnium group 4 elements. And if you look at the properties of these two materials, in case of niobium moly tantalum tungsten, the material shows excellent properties under compression. And if you look at the strength under compression, you can see this material actually retains about 400 megapascal up to 1600 degrees C, which is far better compared to existing nickel-based superalloys or other high temperature materials. So you can see while this material shows excellent properties under compression, but when we test this material under tension, although there are really limited studies that exist under tension, because this material is very difficult to process since you have all these refractories and you cannot get large chunks of material to do properties analysis under tension. Although there are some studies where they investigate single crystal, bicrystal and nanocrystalline film, and the fracture toughness, if you see those values, they are relatively much lower compared to what I was talking about in FCC alloys. And even in case of niobium, tantalum, titanium, hafnium, we see this material actually showing a lot of ductility and uniform strain, about you can see here about 15%. And this material actually fractures by micro wide nucleation and coalescence. So although you have almost similar composition, half of the composition is similar in both these alloys, you see a very big difference in their properties. So that's why I've selected these two examples to highlight what is going on in this material. So starting with niobium, moly, tantalum, tungsten, uh, the challenge is, as I mentioned, processing these alloys. And the reason why for that is you have these high melting point elements, and all these elements actually have very high affinity for oxygen. So it's very difficult to build large samples to do tension tests. So our collaborator in China, IMR, Professor Ely, he was able to come up with this brilliant idea where they kept the bottom half of these blocks of these buttons they produce by arc melting uh, in solid form, and the top they melt it during the process like multiple times. And by doing that, what he's essentially doing is that he's recrystallizing the bottom part. So recrystallizing these materials is very tough. You might have to do like material processing about 1800 or 1850 degrees C, so that these materials don't crack, and then you can recrystallize those. And although these things you have to achieve under extremely high vacuum to avoid oxygen catching. So by doing this process, he was able to form this region of equiax grain in the buttons, where you can see recrystallization as these small grains form on the grain boundary triple points. Although we were able to achieve these equiax grains of, like, you can see 2 mm in thickness and 7 to 8 mm in length, the challenge of oxygen capture we were not able to avoid. And grain boundary had these oxide particles of like pentoxide, niobium 205, or pentoxide tantalum. So we were not able to avoid these oxidation of the grain boundary or formation of oxides on the grain boundary, but we were able to achieve these equivalent microstructure. So we went ahead and uh, we evaluated the properties of this material under tension. So looking at compression behavior of this material, we see this material shows excellent strength retention up to 1200 degrees C, and there is significant plasticity also under compression, as it has been reported by several people. But if we look at the properties under tension, this is where we see the contrast. Now material fails before yielding at all temperatures, and the tensile true stress doesn't go even higher than 70 megapascal. And if you look at ductility under tension is less than 0.04%. So it's abysmal when you test these material under tension. So we had these microstructure which are equiaxed as well as columnar grains ahead of the crack tip. So we went ahead and we evaluated the fracture toughness of this material different microstructures at different temperature. So we found this interesting properties in this or fracture toughness values in this material. At room temperature, you can see this is the data from literature. The EQX microstructure shows a fracture toughness about 4 megapascal root meter, and columnar microstructure shows actually much higher fracture toughness at room temperature. But as you increase the temperature, you see the fracture toughness of columnar microstructure goes down, and EQ microstructure shows higher fracture toughness as the temperature is uh, increased. So this was really interesting to us, and we wanted to understand what is exactly going on. So we looked at the fracture surface of this material, and we see that at room temperature the material fractures by these cleavage fractures, but with increasing temperature you can see uh, the fracture mode is now mixture of cleavage and intergranular. At 800 degrees C, at 1200 degrees C, we see complete intergranular fracture, and you can see here that these cracks, actually these river marks, emanate from the grain boundary. So there is something going on the grain boundary, and at higher temperature grain boundary is so weak that we are getting intergranular fracture. So we went ahead and we looked at the grain boundary of this material with this in situ TM experiments, where we take these grain boundary oxide phase and we heat it up to higher temperature, about 1000 degrees C. So by the time we reach let me speed this up, 800 degrees C, you can see no significant change in the grain boundary precipitates. But as we go temperature higher, about 900 degrees C, you can still see the grain boundary phase is almost stable. But when we keep this material for a few seconds at 900 degrees C, you can see the oxygen starts to diffuse outside, and you can see the size of this oxide particles is reduced. And by the time we reach 1000 degrees C, the oxide particles completely disintegrates inside the material. So this is the change in the characteristic of the grain boundary particle is what we think is controlling this fracture mechanism, where you see room temperature you have cleavage fracture, but higher temperature you have intergranular fracture. And it is also known that these oxide phase, grain pentaoxide phase, they go through this polymorphic change about 800 degrees C, and by around 1200 to 1300 degrees C is when they melt. So this indicates what is the reason for this change in interesting change in mechanism of fracture. Although we were able to understand what is going on with the fracture surface, we were still wanted to rationalize what is the reason for differences in the fracture toughness values. So if we think of fracture at ambient temperature, which is happening in transgranular fracture mode, so we can think of Ricci not Ricci model for brittle fracture in Ricci not Rice model for brittle fracture of this material. So what Ricci not Rice model suggests is that ahead of the crack tip you have this stress field, and the stresses from this stress field, if it is higher than the fracture strength of a microstructural weak point ahead of the crack tip, in that case the material will fracture. And in cases where you have high probability of finding these particles, the fracture toughness will be lower. So if we compare these two cases where you have columnar microstructure and EQS microstructure with these grain boundary oxide particles, you can see in case of columnar microstructure, the probability of finding these particles, which are the microstructurally big point for this material, is less compared to EQX microstructures, and that could be the reason why we see such change in fracture resistance with, at the room temperature, or such difference in fracture resistance at the room temperature. But at high temperature, where you are going through this intergranular fracture, the columnar grains, the fracture toughness depends on how these columnar grains are aligned with the direction of crack propagation. And you can see as you increase the theta value, the fracture toughness or fracture resistance also increases. And it is highest in case of PQX microstructure, where with respect to tilting of the crack, you are also having twisting of the crack because of the EQX microstructure, and combination of both gives a highest fracture resistance in EQS microstructure at 1200 degrees C. So this is what explains the fracture resistance in niobium, molybdenum, tungsten. Although we have a very poor fracture resistance, we are able to still recover some fracture resistance through extensive toughening of this material. So coming to the second alloy, which is niobium, tantalum, titanium, hafnium. This material was ductile, as I talked initially, and it was so ductile that we were able to actually cold roll the blocks of this material, and we were able to recrystallize the grains through heat treatment about 1100 degrees C. So we went ahead and we did some tensile test on this material. Uh, at room temperature, it shows uh, uniform strain about 15%. Even at cryogenic temperature, this material is ductile, and we see uniform strain about 10%, which is really surprising for a BCC material, BCC refractory material. At higher temperature, BC will lose a lot of ductility because of intergranular fracture, as I will show in next few slides. But we see that material fractures only after yielding, even at 800 degrees C and 900 degrees C. And at 1200 degrees C also we see material yields before fractures, and we see this strain softening happening here. So because this refractory is only refractory till now, refractory high entropy alloy, where we see some ductility, and we are able to, at even at high temperature, see material yielding. So we can have this yield strength value versus temperature plots, and we can compare this with existing material. So that's what we did. If you look at the this is niobium, tantalum, titanium, hafnium, you can see the starting strength at room temperature is quite low, but the material retains its strength very well up to 1200 degrees C. And now you can see it's almost comparable to single crystal nickel based super alloy at 1200 degrees C. And if you just normalize these strength values, and you can just compare the strength retention, in that case you can see this actually NTTH shows better strength retention compared to the existing materials that we use at high temperature. So this was really interesting. And when we did a fracture resistance evaluation, again R curve evaluation of this material, so when we were trying to evaluate the arc of this material, uh, or the fracture resistance of this material, the challenge was trying to get a valid fracture toughness, because this material shows plasticity even at higher temperature. We had to use J method even at high temperature, and that's a really challenging task, because usually if you have done J test, even doing J test at room temperature is challenging, but we had to do the J test at very high temperature. So the existing method of using elastic compliance or unloading compliance to measure crack length was not really working. So we had to use this normalization method, which is mentioned in the ASTM 1820, to get a JR curve at higher temperatures. And if you zoom in this region, so at room temperature, you can see R curve goes really steeply up, and after this value we did not have valid J value, but you can see even here the J value has almost reached 500 kilojoule per meter square. And if you look at these other temperatures, you can see the fracture resistance is, or rising R curve at all temperatures. And you can see even at cryogenic temperature, usually all refractory materials, usually they have this ductile to brittle transition temperature above room temperature. But in this material, you can see that it's still showing rising R curve at cryogenic temperature. So that was really interesting to see that we have not actually reached a ductile to brittle transition temperature of this material even at 77 Kelvin. So when we look at the fracture toughness values of this material, we see the fracture toughness value KJ1C is actually higher than 50 megapascal root meter at all temperatures, and at room temperature is even higher than 250 megapascal root meter, which is comparable to FCC materials. This is where all the BCC refractory high entropy alloys or BCC alloys lie in the fracture toughness versus yield strength plot. But you can see this is where NTTS lies at room temperature. So that was really surprising. And if you compare these values to a fracture toughness of niobium, moly, tantalum, tungsten, you can instantly see the difference in fracture resistance of this alloy, which all I should mention here that which almost have similar composition, and you have only exchanged a couple of elements here. So where is this fracture resistance in this material is coming from? So again, to understand that, we took the CT samples and we sectioned it from the center to expose the region
Punit,
of high.
we're at 1 hour. Maybe you can finish up in 5 minutes so we have some time for discussions.
Yeah, definitely. Yeah, I'm coming to my end of my presentation.
Thank
Yeah.
you.
Yeah. So what we see here is that you have at the crack tip, you have a formation of these kink bands. You have a lot of these kink bands. So what are the kink bands? The kink bands are uh, when you apply stresses on this material, kink bands form by lining a lot of edge dislocations, and which rotates the crystal itself. And the rotation of the crystal is such that the crystal is rotating in direction of maximum critical edge of shear stress. And by doing that, you are maximizing the plasticity inside the material. And essentially, kink band formation is a strain localization process by which you get strain softening. And but in this case, you can see at all temperatures, formation of kink band is the process by which the damage is spread away from the crack tip, giving you such high fracture resistance at all temperatures. Even at high temperature, where you can see this intergranular fracture, in these cases also you can see formation of these kink bands. Although your grain boundary has weakened by exposure to oxygen, you can see these plasticity, and that's why you have such high fracture resistance in this material. At 1200 degrees C, we saw recrystallization started, which means the microstructure is not really stable at 1200 degrees C, and that's what gives you such high blunting at 1200 degrees C. So we wanted to understand what is kink band. The kink band, the idea of kink band first given by Orwan in 1948, and he talked about kink band aligning edge dislocations which rotates the crystal. But it was not really confirmed if the edge dislocation is what is forming these kink bands by lining up. So we did these 4D stem experiments where we wanted to see what is happening across the kink band boundary, and we wanted to see if they are pure tilt boundary or pure twist boundary to confirm if they are made by edge dislocation. And this 4D stem, if you look at there, you can see a distribution of misorientation is different from one location to other location, and which suggests that edge dislocation doesn't perfectly line up everywhere to give you this perfect tilt boundary. But from this diffraction pattern, we did confirm that kink band boundaries are a tilt boundary. And because of this formation of kink bands, if you look at the fracture surface, fracture mechanism changes from cleavage to microvoid coalescence to intergranular fracture at high temperature. In all these cases, because kink band is driving damage away from the crack tip, you are getting higher fracture resistance. So that was really interesting to see. So we looked away from the crack tip also to understand what is happening with the deformation mechanism. And in this region, we see presence of both screw mixed and edge dislocation. And this is a bit interesting for high entropy alloy community, because people say that lattice distortion in high entropy alloy slows down the speed of the edge dislocation, and we do see some edge dislocation in the material, which suggests that the velocity of edge dislocation has really slowed down. We also saw twinning happening at all different temperatures, so that was also really interesting. So coming to the conclusion of my talk, the first part where I talked about niobium, molybdenum, tungsten, it shows that refractory high entropy alloys, before we claim that they are the structural materials for future, we need to evaluate their actual ductility and test them in tension. And in some cases, if your material is really brittle, like niobium, moly, tantalum, tungsten, intrinsically brittle, you can improve the fracture toughness by extrinsic toughening. Niobium, tantalum, titanium, hafnium refractory high entropy alloy is really interesting because it shows exceptional fracture resistance, which is derived from this mechanism which promotes strain softening. Kink band formation is a strain softening mechanism, and it gives you really high fracture toughness. And this is really opposite to what we see in FCC high entropy alloy, where you have this extensive strain hardening, which resists a nucleation of these microvoids and gives you high fracture resistance. In this case, you have a strain softening mechanism, kink band formation ahead of the crack tip, which is able to spread the damage away from the crack tip and give you a high fracture resistance. So with that, I would like to thank my team, Professor Rob Ricci, Mark Ashta, Andrew Miner, and PhD students of my team, as well as my collaborators for all their help. Thank you, and I'm ready for questions.
Thank you very much, Dr. Punit Kumar. That was wonderful. You bridged all the way several various topics, packed, well packed within the last hour. So let's see if we have any questions from the audience. Please raise your hands and I'll ask in the order that I see on my screen. We'll begin with Dr. Deepa Srinivasan. Deepa.
Yeah, thank you very much, Dr. Punit. That was, like Dr. Namrita said, it was a lot of information on many topics. My question was the very first part, very first alloy titanium niobium. You showed all those nice cleavage fracture, but you did also mention that there were micro pores. So, quick question on that is, I didn't see that coming into the picture in the mechanism. Typically, in additive, we do speak a lot about the variable porosity, right? So, any thoughts on that or comments?
Yeah, so we were able to actually reduce a porosity below 0.5%. And usually, fracture toughness, when the test you are doing, you are exposing really small volume of material ahead of the crack tip. And if they don't have that much porosity, it doesn't play that much role. But in this case, actually, niobium, unmelted niobium played a bigger role compared to what you would expect from porosity, because the porosity was reduced significantly. And when you have unmelted niobium, it also had effect on the mechanism of deformation, because of the stability of beta titanium or beta phase in titanium depends on how much niobium you have inside the solid solution.
Sure. Thank you. Yeah.
Thank you. There's a second question from Dr. Abhinav Arya. Please unmute yourself. Thank you.
Yeah. Hi, Punit. Yeah, it's a great talk and good work. Uh, my question is, like, in the end, you said that these kink bands are responsible for increasing the fracture toughness, but
Yeah.
like how I understand, kink bands are they should ease the dislocation, or they should be responsible for softening, not increasing. So we can understand that the ductility will increase, but uh, you are saying that the strength is increasing because of this kink band. So this is little counterintuitive.
Very nice question, Abhinav. So, as I mentioned, this is really surprising. As you said, kink band formation is a softening mechanism which should actually strain, soften, and lead to necking. But in this material, what happens is that we form a lot of these kink bands, and kink band has a slight difference from other softening mechanism or strain localization mechanism, is that when you increase the strain, usually other strain localization mechanism, you will keep localizing a strain at the same location, and you eventually will create a fracture or crack there, and material will fracture. But kink bands are uh, a mechanism where if you increase the strain, the kink band, the misorientation across the kink band boundary will keep increasing until it reaches the maximum direction of maximum critical resolved shear stress, and it locks up there. And when it locks up there, in this alloy we are seeing that lot of kink bands nucleate. So you keep nucleating more and more of these kink bands, that becomes a driver of plasticity rather than localizing a strain such that leads to nucleation of micro voids or cracks that can affect the fracture resistance. And as you said, the ductility is affected by these formation of kink band. The strength of this material is also lower because we can nucleate these kink bands, and ductility is affected. So what we think from our theory is that if you look at these dislocation activity, so in the region where we see uniform strain, the strain hardening is driven by this dislocation activity. And once you reach these regions, you start nucleating the kink band. Now your material starts to necking, and this region is driven by kink band formation. And that's what we believe, that in this region uniform strain is driven by these dislocation interaction, but necking is driven by kink band during tensile deformation. But in case of fracture, when you have a crack tip, the material becomes really the mechanism becomes really interesting, because now you can nucleate more and more kink bands, like this amount of kink bands. Usually kink bands have been investigated in single crystals, nano wires, and you see some kink band forming, and that's where strain localized. But in this case, you can nucleate a lot of kink bands in the same grain, and kink band also interact with each other, like kink band ends on the another kink band. And that is happening because it's something related to the atomic level of mixing of these elements that we have done this in this case. Yeah, thank you.
Yeah. One more question I have.
Go ahead.
So in your first part of the talk, you showed that honeycombs, because of that honeycomb structure, you were getting good mechanical property. But if we look at the 3D structure, it was kind of a columnar microstructure. So in the other orientation or in the other direction, was there any loss of the properties or loss of mechanical strength and other things?
So that's another very good question. So if you look at the honeycomb microstructure I showed, sorry, let me go to that. Yeah, so the dimension of this honeycomb, if you look, is really small. So essentially this picture is from one grain, and inside a grain, the honeycomb grows like rods. But if you have different grains, your orientation of these rods would be different. So it's not like we are testing rods of columnar long rods in one direction. But you are right, there would be some effect if we test in other direction, because the material is highly textured. But we have not done the tests in other direction. We have just tested in one direction.
Oh, yeah. Thank you.
Thank you. There's another question in the chat box along the same lines of the honeycomb structure from Dr. Chandan Kumar. He says, in the honeycomb structure, the materials fail at the grain boundary. What heat treatment did you choose so that the B2 phase migrated inside the grain?
I'm not sure what he means by, Dr. Chandan means by material failing at the grain boundary. We don't see that, but
If Dr. Chandan is still there, can you please unmute yourself and maybe you can clarify what you mean by that question?
I was asking like this during cryo test, like fractograph you have. So it fails on grain boundary along, means at B2 phase boundary.
So I don't think I've shown it doesn't fail on B2 phase boundary. I haven't shown a fractograph. Uh, it doesn't fail on B because there is not large difference between the strength of the B2 phase and the matrix. So the deformation actually happens in both, uh, mostly happens in the matrix, but we don't see such a strain localization happening, and so that the crack would nucleate on these boundaries. But that can happen. Essentially, in the end, that's how the material will fracture. After a lot of these deformation that materials induce before the crack nucleates on the B2 phase boundary. And we were able to, I think the second part of your question is that how do we achieve this microstructure during the heat treatment. So these microstructure is a FCC material. Is not really a stable microstructure, because we are doing this fast cooling during laser powder bed fusion process. So if we do annealing treatment about 700 degrees C for 1 hour, we can essentially dissolve this B2 phase inside the matrix, and we can form these precipitates by doing fast cooling.
Thank you. There's a next question by Dr. Sitaraman.
Yeah, nice. We had a wonderful lecture, Dr. Punit. Thank you so much. I don't have a question, but only few very small observations. What we had long back during 70s when we were trying to, Dr. Guprakash knows about this, these ductile irons where you have a lot of spheroids. At that time, we are concentrating more on the CTOD to improve the toughness, concentrating on variation in silicon as well as the cooling rate. So when we increase the cooling rate, one aspect we're looking at the convection currents. Convection currents ahead of any straining, for example, crack tip. So the crack tip seem to be a storage of many things. I think it could lead to some chaotic things, some reasonably good things. I think the kink bands, what you expressed, is really good, and this, especially the addition of aluminum in iron and cooling it very heavily, I think also gave something like this. But we did not continue the work, and the microscopic observations were limited to only the microscope, and which during 70s about it. So I think this analysis what you made is really wonderful. I think we will stay in touch. I think
Thank you very much.
very, very nice, very nice. Kink band theory really like it very much. I think it's CTOD. I think if you look at CTOD very sharply, I think maybe there is some good modeling. I think will come out. Let me
Yeah,
also
definitely.
touch with you. Yeah. Thank you. Thank you so much again.
Thank you.
Thank
Thank
you.
you.
There is no other question. I had one question. I'll take the opportunity to ask my question. So you showed these niobium alloys in your part two, what you called at the talk, where you showed these columnar geometries, and you had done your studies at room temperature 800 and 1200 degrees Celsius.
Yeah.
There was one more plot after this where you showed the changes, and you'd um, after this. Yeah, this one. Let's stay here. So, no, the previous slide, please. The previous slide.
This one.
Yeah, here. So I was wondering, so actually, if you look at it, the fracture toughness is not, I assume this was one sample that you have tested at 800 and 1200, right? So, and you probably kept it for some amount of time. So there looks like there's a lot of variance in your data at 1200. And there's not much difference in the 1200 and 800, actually, although you draw this line like so. Um, do you want to comment on what is the role? And you also show these lovely TM data of how, these you had these very nice videos of looking at how those structures changed at high temperature. So what do you think is the role of equilibrating the material over longer time durations? So let's say time is a factor. How much of a role do you think the changes like what you're showing is this very sharp curve. Do you think that the variance could become even more different or at these temperatures? So you might not find much change um, between 0 degrees or whatever at room temperature and at high temperatures.
Yeah. So I think that's a really nice question. So uh, if you look at the fracture, so I think you are right about not having enough data to actually comment on uh, how different it is. But basically what I was why we were doing that is because if you look at these data values, and at room temperature we got similar data value to what we get in nanocrystalline materials for the fracture toughness. And if you compare, so we did do like multiple tests here, 3 tests for EQS microstructure, and columnar microstructure we did like so the challenge with these tests was that we did not know how the microstructure ahead of the crack tip looks
Yeah,
before we actually fractured the sample and looked later on. So we were not able to choose which sample is for which condition. We were only able to like post facto say that, oh, this sample is for this condition. So that's why we ended up doing multiple tests for certain temperature, but for certain temperature we did not have multiple tests. But with respect to the values equilibrating when you keep this material at longer time, so there was one basic difference in terms of the TM experiment we did. So in TM experiment, we see that these oxide particles actually dissolves around 900 degrees C.
hmm
So what we did is like we took some of this material and we heated up to our test condition about 1200 degrees C, and we kept it there for the whole test period without applying any stress, and we cooled it down, and we looked at the microstructure again, and we see that there was not much change in the morphology or types of oxide that was on the grain boundary. So in TEM, because you have these high vacuum, and you are using
yeah,
high electron volt of these electrons at high electron volts, you degas these oxygen from the uh, oxide particles
right,
around
right.
850 degrees or 900 when polymorphic change happens. But when you are not applying any stresses inside the material, the oxygen is not actually going out from this oxide phase. Their structure changes. We don't have any verification of that, but that's our theory, that a structure changes, but when you cool down, the structure again reforms.
Understood. Understood. Okay. Yeah, that's very interesting. Okay, we'll take one last question from Dr. Suraj Kumar.
Yeah,
Please
hello. Yeah,
unmute yourself.
thank you
Yeah.
for
Okay, let's try that again.
Sorry, yeah. Am I audible now?
Now you're audible. Yes, go ahead.
Yeah. So I had few basic questions. Yeah, nice presentation, Dr. Punit. So how you are measuring the strain at 1200 degrees centigrade?
So the strain in terms of tensile test or CTOD for during the fracture toughness test, if you can clarify that.
Tensile testing, how you are
Tensile.
measuring?
Okay. Okay. So we were measuring the strain using the extensometer. We had this high temperature extensometer which goes inside the furnace, long ceramic prongs. But because material fractured in the yield section, yield region, we were not able to actually get really significant data out of that extensometer. So we just use the load line displacement for those strain values, but we corrected it to modulus, elastic modulus on the material that we measured using this ultrasonic method. uh, we have these small probes that you can put on the samples and you can measure their elastic modulus.
Okay, and if I'm correct, you are doing all these experiments in some inert or vacuum environment, right?
Yes, we are doing these tests under argon environment. Yeah.
Okay, so one more last question, like the dislocation types that you are seeing in the second last slide, I think the screw, edge, and mixed type.
Yeah.
So I just want to ask that these are the projection of the lines. I think those are S-time images, hard F images, right?
Yes. Yeah.
So I mean, do you do you want to comment anything on the percentage of this type of dislocations, which is affecting, which is basically controlling the
Uniform.
strain?
Yeah.
Yeah.
Yes, so I think that's a really good question. So we did essentially, like, if you know, if you do TM and you want to identify which type of dislocation it is, you have to do this G dot B analysis, which is really involving, where you have to tilt the samples at multiple angles and try to identify the versus vector of these dislocations. So
Mhm.
because of that, you cannot do, like, we were not able to do analysis to comment on a statistic of amount of age, mix, or screw dislocation types. But we do see these long yeah, we do see these long screws or edges dislocation somewhere, but we cannot comment on the statistic of how much of which forms.
Okay. Yeah. I was actually, yeah. That was my question. Okay.
Yeah.
Thank you.
Well, thank you very much. I don't see any other hands raised, and it's well past time. And so I want to again take this opportunity to thank you, Dr. Punit Kumar, for a wonderful talk and for patiently answering all the questions, especially because it's probably really early. It's now probably at 7 a.m. at your time. So thank you very much. And for the everyone else, thank you for joining in. I'm sure there'll be more talks scheduled from the side of InSIS, so please stay tuned for more news from Professor Raghu Prakash in the coming weeks. So thank you once again, and I'll stop the recording.
Yeah, Namrata, just wanted to thank you. Professor Raghu Prakash asked me to